Oh, okay. So thank you very much for this very nice introduction and for the opportunity to present some of our work. And in fact, part of the work I was presenting was done with by Kevin Jablonka, who was on the program a little bit earlier. And if you look very carefully, the titles of our presentations are very similar, but we try to coordinate it a little bit that you're not really getting things twice. So the focus of my work is a little bit in the context of metal organic frameworks and machine learning and why we do that, and I will focus on explain that a little bit later. But let's first sort of think a little bit about machine learning and why we're doing this. And I just hope that Kevin, because I stole these slides from Kevin, that's sometimes what you do if you're a professor and you have people really getting good ideas. You think, I want to show that too. So this is really due to Kevin. And that is actually, if you do materials research, often people say you want to find a needle in this famous haystack. So here we have the haystack and somewhere there's this magic needle of the material with the properties we're interested in. So here, this is then an example of hydrogen storage, that you would like to have a metal organic framework, and I will come back to what that are later on. And you really would like to find the best material, and you see all those titles from finding a needle in a haystack. And then the first question you can ask is, how do people find a needle in a haystack? And this has been done. And you see two people that were looking for needles in a haystack, but they're not using machine learning. And let's think a little bit about that. Why is it that nobody uses machine learning and will never use machine learning to find a needle in a haystack? So if you think about it, what is the importance of machine learning? So machine learning that tries to recognize patterns, tries to recognize similarity, tries to recognize what is actually going on. But if you think about it, what type of information we can learn from the haystack that tells us where the needle should be? There is no magic that the needle influences the haystack in such a way that if you learn something about the properties of the haystack, that will tell you there will the needle be. So the haystack, if you think about it, if you now replace the haystack by chemical space, by materials design. If you do chemistry, you all have had that in high school. You combine atoms, and that space is not like the haystack, it's highly structured. So what you want to do in machine learning is learn about the structure of the space and translate that learning into finding the needle. But you see, you can't do that in the haystack, but what we will see is you can actually do that in the chemical space. Then there's another issue you have to take into account, that if you think about machine learning, the idea is we can solve every problem if we have enough data. So, so some of you must have generated those images with DALL-E, with these open AI ideas. And the way they created those images, and that was also the Nobel Prize in Physics was actually very much related to that topic, is you train a model on trillions of images. And from that information, how you learn very simple things, that if you look at a hand has 5 fingers. That's not something these programs know. It has been taught to them by just having many images. Well, if you sort of think about chemistry, we always are in what we call the small data regime. You can say people can take millions of pictures and you collect them on the internet, so you have many examples. But if you need to do chemical experiments, it's actually a lot of work. So yes, there's a lot of data, but not all that data gets published, and it's never enough for machine learning. So we always need to add a little bit. And that is what we would call leveraging. You always need to leverage something. So what you can do, for example, if you want to describe a problem, you use descriptors in machine learning that basically are already informative of what we know. For example, if you do a chemical reaction, you know that in most cases, it doesn't depend on the position of the moon. So if you want to make a descriptor that describes chemical reactions, you probably don't want to use data that relates to the position of the moon. You just know that is not relevant. So what you try to do is you use all your chemical knowledge to make descriptors of the problem that are as closely as possible to what we all know about the chemistry, so we can use the little data we have to train the relevant part, and we don't need a lot of data to remove the irrelevant part from these descriptors. What you will also see is how you can augment data with computational techniques. For example, if you use molecular simulations, that a field where I know a lot about, you can predict vapor-liquid equilibria, or calculate properties of materials like the viscosity and those kind of things. That is something you can actually do relatively fast with those computers. You don't have to do the experiments, you don't have to make the materials, you just do everything on computer. And some of those models are actually sufficiently accurate that you can believe those results, that they reproduce experiments quite well. And in that way, we use computational methods to generate a lot of data. Where I would like to talk about, and that is sort of the background, is it's transfer learning. And what is the idea? Is there we train a machine learning model with a lot of data, but not with data that is we want to know, or we know, but with the data we have. And what you then need to have in mind is we have a lot of data, which is easy to, for example, to generate with computational methods, but we're really interested in an experimental question. And then the question is, can we leverage that information we have to solve a problem where we have far less data for? And that is actually the thing I would like to talk about, how to leverage data. And that is work which Kevin also talked about, which we have recently published, and it's about leveraging large language models. But I would like to go there in two steps. So first, and I think since this entire meeting is about large language models, the beginning will be sort of a recap that basically I just want to tell you how I look at these language models. And before doing that, let's first talk about the materials we are interested in and why machine learning is so important in these materials. So the question we are interested in, and I will explain the context a little bit later, is in metal organic frameworks. So metal organic frameworks are crystalline materials, and you see here a computer graphics where you have a metal node, the blue part, that is connected with a linker to another metal node. And what you see here, it forms a very nice crystalline material. And these dimensions of the pores that are formed, so here are pores, and gas molecules can be absorbed in those pores. And what we would like to do is we would like to use these materials for carbon capture. That is, if you burn fossil energy, fossil fuels, or if you make steel, or if you make cement, or with waste incineration, you have CO2 in the flue gas. And what we would like to do is we would like to design a material that is optimum to capture the CO2. Then if you capture the CO2, you can use geological storage to avoid the CO2 getting in the atmosphere And everybody has sort of heard about climate change. So these materials may be very interesting in reducing the cost of carbon capture and making that more acceptable. Now, what makes those materials so interesting from a machine learning point of view is the enormous chemical tunability. So what you can do is you can change the metal. So you can have different metals here. You can change the linkers. And you can change these linkers. And this is just a few examples of what chemists can do. And you can also, the way you put the metal nodes and the linkers together, and that's called the pore topology. And that is characterized with these nets. And if you then make a back of the envelope calculation, you can sort of make trillions of possible materials. And the question we are interested in is then, what is the best material for carbon capture? And you sort of see this is way too many materials for to experimentally synthesize, to test. Because if you do this in the lab, and let's suppose we have an idea, we want to make this metal organic framework. And then you have to make the linker, you have to find the metal node, you have to find the right conditions that they crystallize. Then you have to measure the crystal structure, you have to measure isotherms, and then you can sort of say, too bad, this one is not good enough for carbon capture. That process takes a few months. So if you are a very good PhD student or researcher in the lab, you may be able in a year to make 4 to 6 of those materials. But there are trillions of it. So even if everybody would be actively making and trying those, we wouldn't have the bandwidth to test them all. So what we then try to do is we try to generate those materials in silicon, to augment the data. So we have the metal nodes, we put them together, and we predict the properties. And that is something you don't then want to use. So how, and now is this questions, how do language models play a role in leveraging information? So let's look a little bit more carefully. What do I mean with a language model? And this is something you already must have had these days. But okay, but at least this is my understanding of a language model. So if you type this on your iPhone, it's really interesting because if I would think about this, I would take a dictionary and look what are the most after feature, what are the words that the dictionary would say start with F-E-A-T. And you would have feathers, or feast, or feedly. But why does it suggest something that makes sense? And the reason is because this is sort of a typical application of a language model. And that is, so the way you can make such an app is you pre-train a transformer architecture, that's what they call. So you let it read an enormous amount of text, English text. And basically what you want to make in a model is you want to predict in the context of this this sentence, what is the next letter? And the way you do it is you basically, from the pre-training of all the English texts you have seen, you just make a ranking, what are the different letters. And then you, for example, see in the context of the words, how do I turn off this? That feathers and those kind of things are far less common in such a sentence than feature. So the U gets the highest probability in that context. So what you do, you basically leverage all the text, all the English text you have learned in order to write this application. So now the question is, how can we do this in the context of metal organic frameworks? So can we do something similar? So what we do here in this work, and this is work we have done with a former postdoc of mine who's now a full professor in Korea, in KAIST, and that is, can we develop a grammar of a language of that speak MOFs? So what we do is we're going to construct sentences that sentences which we use to pre-train a language models. So what we do is we take a MOF structure and we convert that into a string of characters. So how do we do that? Huh? You take the structure of the MOF, you then decompose it in what are the chemicals, what is the pore structure, and everything gets translated into a character. And there's sort of a one-to-one mapping of the pore structure into characters. So more or less the way you should see it is we take a MOF structure. Sorry, I went in the wrong direction. We take a MOF structure, we convert that MOF structure in a unique way into a set of characters, and we add some properties to it, like the MOF topology, the void fraction, and the organic linker classification. So that is the same as the English text we had to pre-train this model on the iPhone. We now have an enormous number of sentences, which is basically a MOF with some properties. Then we pre-train a language model that can that has learned these kind of things. And what you do then is you fine-tune that with properties for which you would like to know, but you have far less data from. So just to give you an idea, this is pre-trained with over 100,000 different MOFs that are all being generated in a computer. And now we're interested in the diffusion of hydrogen in these materials, the oxygen diffusion, and the band gap. And these are properties that are completely different. But what you hope that in the pre-training, we know already a lot of the material, and that knowledge we can leverage. And I hope you sort of get this idea that we are interested in a property, but we don't have enough data to really train a machine learning model from scratch. So what we do here is we build up a knowledge base of these metal organic frameworks, which is all computer generated. It's an enormous database, and that has been pre-trained. And then we fine tune that model with a little bit of data of what we have. So in here you for example, see the results of the pre-training. So basically, this is some of the structural properties. This is the void fraction. So you see if you visualize this, this pre-training was successful. And this is now, if you now think every dot is a material, if you now think back about the haystack, you see we now have a space that has structure. You see we can color common materials and they all cluster together. You can color the void fraction and you see it all clusters together. So by this pre-training, and that is what you do, you have all these sentences of a MOF and some properties. You pre-train it and you see, if you analyze your pre-training network, you see this network has structure. And it's that structure you then leverage to do something we don't have enough experimental data for. And the way you do that is basically it's what you call transfer learning. So you train a network, a neural network, and what you basically do is you freeze part of the network, and you just retrain the top layer or with data. So the hope is, and the idea is that you freeze the knowledge, but you fine tune it with the data we have. Now let's see how that works. Okay, so here we have the three properties. That is the diffusion of hydrogen, the uptake of hydrogen, the diffusion of hydrogen, and the band gap. These are properties we have data from, but not enough to fully train a machine learning model. And what we do see here is the size of the data set. And here is a measure of the accuracy of the error we make. This is a model that has been trained, but it has a high error. Here it gets better and better, and the open symbols are our results. And basically what it shows, that we have the highest accuracy with the least amount of data for all these properties. And then basically what this is telling us, this idea of leveraging knowledge works. Because if you would, these are these typical models that are machine learned from scratch, but we already get quite much better results because we can leverage our pre-training. Okay, and this is also work we published quite recently. But you have to realize this is actually quite a lot of work, because you have to collect this enormous database of over 100,000 MOFs with properties. You have to pre-train a transformer model, and then you have to fine-tune it. So that is a lot of work. So we were wondering, actually, Kevin was the idea. He basically sort of said, instead of this, can we not leverage something else? And that is GPT-3. And GPT-3 is also a language model, but while we trained our language models of this MOF grammar we developed ourselves, GPT-3 is trained on everything you can sort of see in the internet. But there is an important caveat. If you look where it's trained on, it's on books, it's on Wikipedia, there are articles in the open literature, but where it's not trained for is everything what is behind the paywall. So if you want to look at an article in a scientific journal, they typically you need to have a subscription. It's behind the paywall. So it's not open access, open science data. So typically you can't, they cannot be seen by OpenAI. So GPT-3 doesn't know much chemistry. And let me illustrate what I mean. So here, sorry, it's to make place for the rest of it, it's in an angle. So here I asked ChatGPT 3.5, what is the phase of terbium half, yttrium half? Now, this is an alloy. It's a metal, a combination of an alloy of two metals. And this is what they call a high entropy alloys. That's an interesting class of novel materials. And you just want to know if it's single phase or multi-phase. It's a very simple chemical question. And this is the answer you get from GPT-3. It knows it's an high entropy alloy, but it cannot extract the phase. It knows it's an alloy, but you really have to know the chemical knowledge better to determine the exact phase of this. So, and this is what many people have noticed, it doesn't know a lot of modern chemistry. So they see ChatGPT as pretty useless. However, you can use it in a slightly different way. And that is, you can fine-tune it, like we did before with the experimental data, with the data. And in this particular case, what we do is we collected data on high entropy alloys, and we know whether that is multi-phase or single phase. So this is the experimental data we collected of some of the high entropy alloys, since this is a language model, ChatGPT, we need to convert this into a question. So here are the way we convert that into a question. What is the phase of this high entropy alloys? Hey, you see some examples, and here's the answer. It's multi-phase or single phase. So this is in terms of how to say a machine learning classification problem. It's just a 0 or 1. So from a text completion point of view, so what we now are going to do is we're going to use these questions, we collect them, and we send them to OpenAI. And we get back a model, a new fine-tuned GPT type of model that is geared to answer this question. And the only answer we allowed is 0 or 1, multi-phase or single phase. So it's important you see what we do. we don't ask this question because that's what we did and said we don't have an answer. No, what we're going to do is we're going to collect experimental data to fine tune or to develop a new machine learning model. And that looks like this. So now you can ask the question and you get an answer now, you get 0 or 1. And now it's interesting to compare that with the state of the art. So what we have here is the accuracy of the question. So what you can typically see if you're here, that out of 88% of the cases, we have it right. So what is the benchmark? You can take me as a benchmark. If I look at these high entropy alloys, I have really a 50% chance of having it right. And so you basically see that is the benchmark, and the machine learning model is doing it better. This is the state of the art. This is the best machine learning model developed for this problem. And you see, if we, this GPT-3, if we have more than 50 data points in our training set, we do better. And when I was seeing these results from Kevin, I was actually amazed. In the sense that how is it possible that this works? Because you have to realize we don't know anything about high entropy alloys. The only thing we did was collecting the experimental data and fine-tuned the language model. While here, this is this model has been developed by a group, and it may have taken them several months to get here, and it took us 5 minutes to generate this curve. So then the real message to Kevin was, this is too good to be true. Go back and show why you're just lucky. Well, he took that actually very serious. So he looked at many other questions, and we came to very similar conclusions. So then I thought, and that is just work which got very recently accepted, let's see how it works. And this time it was, we started when it was still called Twitter. Let's see if it also works for problems we don't invent. So typically what we did in our first work is we looked at data sets that were previously used for machine learning, so we could benchmark our method. So what we're thinking here, why don't we ask the community, do you have a problem with some which involved chemistry? And we help you fine-tuning a model, and we will learn something from it. And it's really interesting. We got data sets of properties of materials, chemical reactions, performing as the device. And we really did it very simple, a very simple classification, good or bad, high, low. And we had as a benchmark random guessing. So it was me, the reference model. So what we also then did is we made sure we had a balanced data set. 50% of the data was good, 50% of the data was bad. So that's sort of the idea. And what I would like to do now is to give you some overview of the type of questions we could ask. And so you can see how we use this model. Okay, so this is coming back to metal organic frameworks, because we always had this in mind. Can you do something, for example, for MOF synthesis? Can you predict synthesis conditions? Because that is really an important question where there is not much theory. So this is work from the group of University of Pisa, where they were making a particular MOF, the MOF called MIL 140 with I think with cerium. And so basically, they had 12 variables, 20 experimental data sets. And now this is really interesting, because this is one of the data sets where we could learn something from. Because if you typically look in the literature, chemists are making a new material and they only publish the most successful recipe. And all the recipes that were not so successful, you actually are not published. So with this data set, we had also access to data that were not published, that didn't work. And the interesting thing is, also with these machine learning models, you also need to learn from things that don't work, and not only from data that works. So these are relatively small data sets. But the way we then fine-tune this model is we make again a sentence. What is the success of the synthesis of MIL140A with reaction conditions? And in these reaction conditions, you then put these type of data in. Okay? And here are then the results. This was the data set. Many no's, a little bit of about 16 no's, about 12 yes, where it was successful. And here you then what you then typically do in machine learning, you keep some data away from the training, and you sort of see this is then a confusion matrix where we had the experimental label and the predicted label, and if here we did typically 5 experiments, and out of the 5 experiments we got 1 wrong. So you see, with a very small data set, we can already make some predictions on the success of a synthesis. Well, this is a completely different property, and this has to do with proteins. And it's really interesting because this is a group that was interesting in whether proteins phase separate or not. And there was a data set, and the question is, can we predict whether a protein phase separates or not? And this is then the questions we are learning. What is the propensity of to phase separate of a protein? Is it high or low? But now the interesting thing is, this is the sequence that characterizes this protein. And you really wonder, if you put in a sentence protein, you replace it with the complete sequence, whether it could be able to learn something. And we were really very surprised that the results are actually quite good. So here you see the GPT accuracy. It's 83%, 64%, or 95% for the different data sets. And below that, you see the machine learning models that are of comparable accuracy. Again, here, what is the difference? It took a few months to develop the machine learning model, and we did this in 5 minutes. What you can also do is you can look at structural data. So here people measured X-ray diffraction patterns and wanted to deduce, can you get the structure back from such a pattern? Now, it's of course interesting because you have a spectrum. How do you translate that into a sentence? So the way we did that is you basically you have a scattering pattern, and what is the structure, and then the completion is one of those crystal structures. So basically what you do is you sample that. You have, if you have such a diagram, it consists of 2,000 points. You sample it, you just sample 200 points, and the numerical value is your sentence. So what we then do here is, from this sampling, the sentence is basically the scattering pattern. Is you look at the pattern, you just take the value and you just add everything together with commas. So this is now a typical part of the sentence. And also, if you do that, we basically get very good accuracy with fine-tuning our language models. It's all very simple to do. Okay. Again, MOF synthesis, you can do successful recipes, you can fine-tune it, and also here we sort of see we get a reasonable, rate of success. So for example, this is then basically, can we make a MOF at these reaction conditions? Of course, in 30% of the cases we are wrong, but if you don't have an idea, a good idea, being able to do slightly better is already a very good thing. Okay. I would like to finish with a few things which are really, I think, quite remarkable, and that is with photo switches. So until now I had done classification, but what you can also do is regression. And regression is basically more continuous. And here we're interested in the transition. So a photo switch is a molecule. If you shine light on it, it rotates. And if you shine light with a different frequency, it rotates back. So what we would like to do is to predict which is the frequency or the wavelength of the light we need to shine on the molecule that it rotates in this direction, and what is the frequency of the light you need to shine on it when it rotates back. And these are the pi star and the transition wavelength, they're called. And now we represent a molecule with a smile string. And this is basically a sentence that represents such a molecule. So if we do that, we can predict the transition wavelength, and it actually goes very well. And here you see an example of the number of training points, how we need to, with the different representations. So we see we're not as good as the dedicated machine learning models, but we do actually quite well. But now it's an interesting thing what we can do is we can invert the questions. So what is a photo switch with transition wavelengths of 3.2524 nanometers? And this is what you would call an inverse design problem. And you have to fine tune it. And what is then interesting is the pale violet structures that are those are structures that could not be found in a database. So apparently, this fine-tuning of GPT-3 is giving us new chemistry. And the interesting thing is you have to be playing with the temperature of the model. Now, let me explain that. So the way these language models works is it will make a ranking. If you want to do a sentence completion, it ranks the next word in a sentence according to the probabilities that these words occur in English text. So if you choose to do that at the lowest temperature, it will also always choose the most common option. And if you then would write the text with that, it would look robotic, because it would always use the same constructions, the same words. It's a very so what you do in writing, say, sort of a summary, they increase the temperatures. So you use synonyms, slightly different sentence constructions. So it becomes a more creative writer. That's what we do here as well. We have to increase the temperature a little bit, because otherwise we would only get the green structures, the structures that are in the training set. If you increase your temperature too much, it becomes so creative, but then the chemistry gets nonsense. So you need to equilibrate your chemistry that you don't make too much nonsense, but it becomes quite creative. And this is really simple to do. Why is this so important? Because all chemistry is about text. So people tend to write a recipe, and in those machine learning models, you can just put, in these language models, you can just put the recipe. And if you think about how to convert a recipe into conventional descriptors, it's really very difficult. So this is a much more natural way for chemists to progress. So this is sort of the last stage of the last slide of my presentation. And this is just some personal thoughts. So basically, can you say, is AI important? I think it's very important for chemistry, but what we will see now is, and we are now in this stage, that AI is promising the sky and the moon. Everything can be solved with AI at the moment, and there's a lot of interest in it, and everybody wants to do AI. Then people will realize that we won't be able to deliver the sky and the moon with AI, so it will fall down, and it will eventually equilibrate to normal levels. So what you also see is people will be very skeptical about AI, because many people will see it as a black box. Just feed in enough data and you don't have to think anymore. For me, it's just another tool to solve problems, and it's a very powerful tool, and we use it among many other tools. So for me, AI is not the end of science. And really, if you think about it, there is no first law of AI that if you use AI, you need to stop thinking. It's really possible to do AI and think about the problems in a very deep way. It's not incompatible. And surprisingly, AI is not different from experiments or any other science. You have good studies and bad studies. Within the context of chemistry, it's really a pity that most of the chemistry is behind the paywall. So if that becomes accessible to those models, we will learn a lot more. And the most important question is, if you would ask me, why does it work so well? I would have to say, I don't know. And we need your help to solve that. And with that, I would really thank you for your attention.